Okay, today we're going to talk about null hypothesis testing, type 1 and type 2 error, and effect size. And there's a lot of material to cover in this lecture. So rather than simply record it and record the audio and have you cursor through the slides, what I want to do is I'm actually creating a new video just for this lecture. This is a really pretty critical lecture for you to understand because null hypothesis testing represents the foundation of inferential statistics and the culmination of a lot of the conceptual thinking that we've had up until this point. So, when we talk about the law of large numbers, central limit theorem, and so forth, it's all building toward ultimately the inferential testing procedures involved in null hypothesis testing. So what I'd like to do is move relatively quickly through the material. So hang on to your seats and we'll get going. Okay, so what is a hypothesis test? All right, so when we're talking about hypothesis testing, we're talking about a probabilistic and inferential procedure, a series of steps that ultimately enables a researcher to decide whether to accept or reject a scientific statement about the relationship of two variables, usually an independent and a dependent variable. So that's a lot of things to think about right there. But basically, we're talking about a procedure that starts with a research question, right? And eventually moves to using sample data to evaluate a hypothesis about a population. So we start with that question of interest, and this is akin to what you're doing in your research proposal right now, right? You start with a question that is of interest to you, and then you make a prediction, a hypothesis about the relationship between two variables. Now, importantly, this prediction or hypothesis we refer to as the experimental hypothesis. This is what we're really sort of interested in. So, for example, in a lot of my work, I might be interested in whether there's a relationship between how much support a veteran receives at home and subsequent expression of post-traumatic stress disorder, okay, and the magnitude, the severity of that disorder. Well, the two variables there are, the first is the independent variable, that level of support, and the second would be what we call the dependent variable, is the magnitude of the PTSD, and I'm hypothesizing a relationship between the two. Folks that experience low levels of support should show higher levels of post-traumatic stress. Folks who receive high levels of support from family members, the public, and so forth, would show lower levels of post-traumatic stress, and actually that's what occurs in the research literature. So we're going to make a prediction. We call this the experimental hypothesis. Importantly, the experimental hypothesis is not what we test in statistics. We're going to test something called the null hypothesis. Come back to that in just a minute. Okay, then we collect our sample data, and from the sample data, we're going to evaluate a hypothesis, and specifically the null hypothesis. So we've really got two types of hypotheses. H sub 0 is called the null hypothesis, and really the null hypothesis states that there's no relationship between two variables, okay? H sub 1, also sometimes called H sub A, is the alternative hypothesis. And what it states is that there is a relationship. Now, of the two, in statistics, we're going to test the null hypothesis, not the alternative hypothesis. If we reject the null hypothesis, by implication, we're supporting the alternative hypothesis. So that implies a central feature between the null and the alternative hypothesis, and that is that they are mutually exclusive. They cannot both be true simultaneously. So we're either going to accept or reject the null hypothesis. Now, this part here, accept the null hypothesis, we have to be a little careful about the language that we use, okay? We can use accept within this class and so forth. It's not a big deal, but really, probably the best language is fail to reject the null hypothesis. And the reason for that is if we say we accept the null hypothesis, that sounds pretty permanent, right? We're either accepting it or we're rejecting it and so forth. But if we accept the null hypothesis, basically what we've said is, hey, in the population, there is no relationship between two variables. Well, the fact of the matter is we're going to be dealing with sample data, okay? So we have a limited amount of information about the population. And if we collected more information, we might very well change our conclusion about what's going on in the population. So really any given study presents results that are true given the information that you have at the time. And additional information might change your conclusions, right? So rather than say with a degree of finality that we accept the null hypothesis, typically what we'd say is we fail to reject it. In other words, we don't have enough information at this point in time to reject the null, meaning reject the idea that there's no relationship between two variables. So there's a lot of negatives in that sentence, right? And so that's what gets confusing about null hypothesis testing, is you'll hear, double negatives, even triple negatives. But it's all going to make sense in the long run as we kind of go through the slides, okay? But the important part, just to recognize at this point, is that in a research experiment, we set it up so that there are two hypotheses, the null and the alternative. They cannot both be true at the same time. Either one's going to be true or the other's going to be true based on the data we've collected in our sample. Okay, so let's talk about the steps to evaluating a hypothesis. First, we need to state the hypothesis about a population, okay, in terms that are meaningful for an experiment. Then we're going to use the hypothesis to predict the characteristics that the sample should have, okay? Then, ideally, we're going to obtain a random sample from the population. And then we're going to compare the obtained sample data, our results, to the prediction that was made from our hypothesis. Okay, so as I walk through an example here in just a second, keep these 4 steps in mind, because that's really the sequence that we're going to go through to make some determination about the relationship between two variables. So let's walk through an example. Imagine we are interested in whether a pill could make people more intelligent. I'm drinking my coffee. Maybe my coffee is going to make me more intelligent, right? Okay, so hey, wouldn't that be great? If we took a pill, we could boost our IQ. Who wouldn't want to do that, right? Maybe you don't have to go to college. Maybe you can save all that money on tuition at Richmond, right? By simply taking a pill. What a great idea. Okay, so we start with a known population. And by known, what we mean is we kind of know the parameters of what the population will look like, because we know that the mean IQ in the American population is 100 with a standard deviation that's set to 15. So when we say the known population, we're talking about individuals prior to taking the pill. In other words, the normal American population. What we don't know is what the population will look like, okay, what those population parameters will be after individuals take the pill. And the reason we don't know that is because we really don't know the size of the effect of taking the pill. How many IQ points will somebody get a boost in? Will it be 5 points, 10 points, 20 points? We don't know. So what we know is the parameters when people don't take the pill. What we don't know are the parameters when people do take the pill, if the pill is effective. So let's take a look at this distribution right here. This is a distribution of IQ scores. It's a bell-shaped distribution. It has a mu of 100. And on the right side are high IQ scores, and on the left side are low IQ scores. If the pill is effective and boosts IQ, we would expect the mu for individuals who have taken the pill to be higher than the mu for people who don't take the pill. And we're letting sample mean stand in for the population mean. So right now, all we're looking at is the distribution of IQ scores without treatment. Now, we might say, hey, we run our experiment and we find that the sample had a mean of 124. Because it's an unbiased estimate of the population parameter mu, we would then conclude that in the population, individuals, if they took the pill, would have a boost of about 24 points. So the mu for the population of individuals taking the pill would be 124. The population of individuals not taking the pill, their mu would be 100. That's a 24-point difference. That's a pretty substantial effect for taking the pill. Okay. Importantly, though, I've now hypothesized that there are 2 different distributions, right? There's a population distribution for folks who didn't take the pill, but the sample would represent a new population. It's different from our population of untreated individuals in that their IQ is higher. So people who are in our sample represent a different population than what we started with. They represent a population of individuals who have been treated with the pill. So we're not talking about one population anymore. Now we're talking about two populations, each with their own mu. Now, here's sort of an interesting thing. It's important that you understand this. We talked at first about what mu would be when no pill was taken. So this is the untreated population, right? And then we said, okay, if they're treated with the pill and the pill works, maybe we get something that looks like this. Now, we really don't know what the mu is for the treated population because we don't know yet the effect of taking the pill. If we knew that, we wouldn't run the experiment. We just put in 124 there as an example. It could have been 109, could have been 115. We just don't know. What we know is that if the pill has an effect, the mu for the treated population won't be 100, right? Can't be equal to the untreated group. Otherwise, there's no effect at all. Now, the mu for folks who took the pill, but the pill is ineffective, is going to be exactly the same as the mu for individuals prior to taking the pill. This is important. This is basically a statement about what we should expect if there is no treatment effect from the pill. So if the pill did not have an effect, we would not expect a different distribution with a different mu to emerge. In fact, it should look pretty much exactly the same as the distribution of IQ in folks who never took the pill to begin with. Okay, so let's now move on to what's the null hypothesis. Remember, we talked about two hypotheses, the null and the experimental hypothesis. The null hypothesis is demarcated as H sub 0. So when you see H sub 0, always think, okay, that's the statement about the null hypothesis. And it generally states that in the population there is no relationship between the independent variable and the dependent variable. So the null hypothesis is a statement about the population, not about the sample, okay? Now, we're going to use sample data to make inferences about the population, but the null refers to the population. There is no change, for example, in the dependent variable due to the independent variable. That would be consistent with the null hypothesis. In other words, what you're saying is the independent variable had no effect. We can manipulate it, we can change it, we can assign it to some people but not others. We shouldn't see any difference in scores on our dependent measures, okay? So when you say the independent variable does not affect the dependent variable, you're saying any change in the independent variable is not leading to a systematic change in the dependent variable. The dependent variable, by the way, is operationalized and measured in our dependent measure. So our dependent variable in this example is going to be intelligence, okay, IQ. And the dependent measure is the IQ test itself, the measurement of IQ. Okay, so the null says any observed change is the result of sampling error. There's going to be random fluctuations. Again, recall we talked about how you can take infinite samples from a population. We wouldn't expect all those sample means to be equal to the population mean. So there's going to be a variation, just random variation that we can't really account for due to sampling error. The question is going to be, do we see a big enough change in IQ to begin to rule out sampling error as the cause for the difference or for the observed mean difference from the sample in comparison to the population mean? Okay, operationalized for this example, there is no relationship between the pill and the IQ. That would be our statement of the null hypothesis, that there is no relationship between taking the pill and IQ. Therefore, IQ scores for individuals not taking the pill should equal those of individuals who did take the pill. We can formally state that as the null hypothesis implying that mu equals 100, okay? So if you take the pill, no change in IQ scores. Mu should equal 100, and that's true with or without the pill. As long as the pill has no effect, mu should equal 100. So what is the alternative hypothesis? Now, here's the thing. The alternative hypothesis is what we're really interested in, right? It represents our experimental hypothesis. It's probably why we did the research to begin with. We're looking for relationships between variables. And the alternative hypothesis expresses that more clearly than the null hypothesis, because the null says there is no relationship. The alternative says, yeah, I think there is, that the independent variable had an effect on the dependent variable. So we've got to figure out a way to express that in notation. We call it H sub 1. Sometimes you'll see it referred to as H sub A. Both mean the same thing, the alternative hypothesis. So change in the dependent variable is due to change in the independent variable. In other words, there is a relationship between the independent variable and the dependent variable. And the magnitude of what we've observed, meaning that the sample mean is so much different from the population mean, that it's too large to be explained by sampling error. So in our example, we'd say, yeah, there is a relationship between taking the pill and IQ. Therefore, IQ scores for individuals not taking the pill should not equal those of individuals who did take the pill. Again, all these negatives in there, and that's what gets kind of confusing with null hypothesis testing. But we're looking at different means potentially. Now, again, in our example earlier, I said, okay, well, mu could be 124. You get a 24-point boost on IQ. We don't know if that's going to be the case or not, right? That's why we're running an experiment. We want to find out how big that boost is going to be. So the 124 here simply is one possible result. What we do know, though, is that support for the alternative hypothesis is implied when the mean for our sample, which represents a population, is different from 100, does not equal 100. Okay? We don't know exactly what it's going to be, but we would say that it would be consistent with the experimental hypothesis, the alternative hypothesis, if mu did not equal 100. Okay, so from there, what's left to do is to create a meaningful criterion for knowing when our sample mean deviates enough from the population mean for us to conclude that the deviation did not occur due to sampling error. So data are going to provide support for either the null hypothesis or the alternative hypothesis, but not for both simultaneously. In other words, these are mutually exclusive outcomes. Only one can be true at a time. So an important issue is, what is the decision-making criterion? At what point do we draw a cut line and say, hey, any sample mean that deviates X amount from the population mean, oh, there goes my scissors. At what point do we get a significant result, a result that can't really be attributed to sampling error? So we're going to use those scissors. Where's the cut point in our sampling distribution where we feel confident in rejecting the null hypothesis? So how much of a difference in the mu that we observe, which is inferred from our sample mean, is enough to convince us that the difference is not due to sampling error? So the following should be apparent. If the null hypothesis is true, then the sample mean after treatment should be pretty close to the mean prior to treatment. So here's a distribution of IQ scores, right? They have a mean of 100, standard deviation of 15. And we're going to have scores that probably fall somewhere in this range, if the null hypothesis seems to rule the day. Okay, so if we end up with means that kind of fall right in here, we fail to reject the null hypothesis. On the other hand, if we end up with means that are way out in the tails, then we would reject the null hypothesis. Okay. Now, we can't really use a raw score distribution to make this judgment, right? Because we're dealing with a sample. So we're going to have to set up a sampling distribution that takes into account our sample size. But the concept here is pretty much the same. If we end up with means that are way out in the tails, we reject the null. If we end up with means that are really close to what we see as average IQ scores, then we struggle to conclude that the pill had an effect. So for the null to be supported, what we're saying is we're failing to reject the null hypothesis. What that means is sampling error can account for the difference between the sample mean and mu, okay, in our population. And for the null to be rejected, for us to reject the null hypothesis, we're saying, hey, that sample mean falls way out here in the tail. Sampling error cannot account for the difference between our sample mean and the population mean. So that means we have to come up with a meaningful decision-making criterion. So when we say the tails, we mean right out here on the right and then on the left of the sampling distribution. And we need to figure out, well, how much area should be here? Remember, we've gone through the unit normal table. We've been able to show that it's possible using the unit normal table to make very precise observations about the amount of area above and below a given point or z-score on the unit normal table. So the question just becomes, what do we consider a sample mean that is close to the population mean? In other words, in support of the null hypothesis. And what would be a sample mean unlikely to be drawn randomly from the sample distribution, which would be out in the tails? Because if it's unlikely that we would draw a sample mean from the tails of the distribution, then we can't really use chance or sampling error to explain its existence. Or we could, but we say it's a real low probability event that sampling error could account for that observation. So what scientists have done over the years, statisticians in particular, have worked to identify the meaningful size of the tails, the amount of area under the curve in the tails, to allow us to either reject or fail to reject the null hypothesis. And what they came up with, and which is really kind of a custom, is that sample means that fall plus or minus 1.96 z's, standard deviations, from the population mean, they fall into what we call the region of rejection. Okay, that's the shaded area here. Those are low probability sample means to occur. Okay, we're not likely to draw these by chance. So if you imagine that an experiment was run an infinite number of times, okay, and we know that if we run the experiment over and over again, we're not going to have the same sample mean every single time, and there's no guarantee at all that the sample mean will equal the population mean. So we'll get a distribution of sample means. That's our sampling distribution. Okay, sampling distribution, keep in mind, depends upon your sample size. So as your sample size goes up, typically sampling error goes down. So when we talk about this from the perspective of a sampling distribution, what we're saying is, if we observe a sample mean that's way out here in the tail, that had a low probability chance of occurring just randomly. It'd be sort of like dipping your hand into a hat and pulling out a sample mean randomly and finding one way out here in the tails. That's much less likely to occur than finding one in here, right around mu for the population, the untreated population. So statisticians have figured out, let's put 0.025 of the area on the right tail, 0.025 over here. You add those together and you get what's called a critical region of 5% of the curve. It's important because this is our cut line. If a sample mean falls in the shaded area, we call that the critical region or the region of rejection. Then we reject the null hypothesis. We reject the idea that there's no relationship between the two variables. Okay, so let's go back to our example, see how it works. Can the pill make people smarter? We all agree? Good thing. Okay, we're going to have these smart pills. We're going to start by identifying the null and the alternative hypotheses, so we put it into statistical notation. The null hypothesis essentially states mu equals 100. The alternative hypothesis, the experimental hypothesis that we're really interested in, right, is that mu should not equal 100. So that's where we start. Then we're then going to identify the boundary for the critical region. Keep in mind that we want the critical region to represent 5% of the area under the sampling distribution. Okay, we're going to put 0.025 of the area here, 0.025 here. Using a z-table, we know that those z-scores correspond to plus or minus 1.96. So if it's 0.025 here, 0.025 here, we sum those together, that's 0.05. That's the size of the region of rejection. The term that we use for that is alpha. Okay, so if alpha equals 0.05, what we're saying is the size of the region of rejection is 0.05. That's the proportion of area under the curve that is in the region of rejection. It's the same also as saying 5% of the area. The critical value for z, which represents the cut point for rejecting the null hypothesis then, is plus or minus 1.96. So if we obtain a z-score for a sample mean that is greater in magnitude, regardless of direction, greater in magnitude than plus or minus 1.96, then we will reject the null hypothesis. So rejecting the null hypothesis is a good thing from a researcher's perspective, because what you're doing is you're rejecting the notion that there's no relationship between two variables. Okay, so here's our example. Let's say that we have a sample size of 100. We have a population mean of 100. We have a standard deviation in the population of 15. In fact, that's exactly how IQ tests are normed. They have a mean of 100 and a standard deviation of 15. And then let's say we do our study, and the treatment group ends up at the end of the study with measured IQ of 106. Okay? So in the population, we know IQ is 100. In the treatment group, we get 106. So that's bigger than 100. But is it big enough to not be due to sampling error? In other words, how unusual is it for a mean score of 100 or 106 to be observed when sample size is 100? For us to understand that, we have to calculate the standard error of the mean. Okay, so the standard error of the mean is going to tell us how much on average scores should deviate from the mean given a particular sample size, right? So how much should the mean differ from the population mean, the sample mean differ from the population mean on average given a sample size of 100? Okay, easy to calculate. We take sigma, which is the population standard deviation. We take n, which is our sample size, and we get 15 over 100. Whoop, where'd you go? Let's go back. We get 15 over the square root of 100. That becomes 15 over 10 equals 1.50. That's our measure of standard error. Okay, so what does standard error mean? That means, okay, given a sample size of 100, sample means should deviate from the population mean by 1.5 points, plus or minus. So if you were to think of a normal curve, and the sampling distribution is a normal curve, then from -1 standard error to +1 standard error is from 98.5 to 101.5. Does that make sense? Okay, 98.5 is 1.5 IQ points below mu of 100. 101.5 is 1.5 points above the mu of 100. We know, as a property of the normal curve, that 68% of observed scores, in this case means, will fall plus or minus 1 standard error from the mean. Now, if one standard error above the mean is 101.5 and we have a mean of 106, that should tell us something, right? Right away, we're thinking, wow, that's pretty big given what we expect to see in samples of this size. So what we have to do to quantify how big that is to calculate a z-score for the sample mean. Okay, so we take our mean, we subtract out mu, and we divide by standard error. So we have 106 minus 100 divided by 1.5. That works out to 4.0. What does that 4.0 mean? What that 4.0 means is that our sample mean is 4 standard errors above the population mean. That's a lot, right? That takes us way into the tail of the distribution. So our obtained z-score, let's call it z obtained, okay? Our obtained z-score is 4.0. That's greater than the critical value for z, which is required to be surpassed in order to reject the null hypothesis, of plus or minus 1.96. So if we look then to see where this obtained sample mean falls, we throw out our sampling distribution, and then we locate the obtained z, which is going to be well into the shaded region. That means when we make a decision, we're going to say, hey, because the obtained z-score 4.0 is greater than the critical value of z, our cut point of 1.96, we're going to reject the null hypothesis. In other words, we reject the hypothesis that there is no relationship between taking the pill, the independent variable, and IQ, the dependent variable. Okay, that's what we're going to do. If the sample mean had fallen in here, in that middle area in the sampling distribution, we would have failed to reject the null hypothesis. So let's take a look in APA format. As you know, statistics are always presented in a uniform format, and for a z-test, or z-scores, this is a pretty standard expression. It's probably one of the easiest ones, actually. All we do is we report the z that we calculated, in this case 4.0, and then we report the likelihood or probability that we could account for an observation of this magnitude due to sampling error. Okay? Now keep in mind, alpha, the size of the region of rejection, was 0.05. So, because our sample mean fell well within the region of rejection, which is defined in size as 5% of the area under the curve, what that means is that the p-value, the probability that we would observe a z-score of 4.0 because of sampling error, right? Because we're plotting this sample mean into a sampling distribution. The probability that we would observe a z of this magnitude due to sampling error is less than 5 in 100. Has to be, right? Because the region of rejection accounts for 5% of the area. This z falls well within that region. So the p-value has to be less than 5 in 100. So p refers to the probability that a sample mean of z equals 4.0 would have been drawn from the distribution of sample means represented by the null hypothesis. In other words, the sampling distribution. What's the likelihood that we would just draw it out of that distribution? Less than 5 in 100. And if it's less than 5 in 100, what we think is that the sample, because it's showing an effect of the pill, represents a different population. That population now is a population of individuals who have been treated by the pill, which has increased their IQ score, right? And they look different. They're a different population than people who've been treated by the pill and it's done nothing, or who haven't been treated at all. So because the alpha level was set to 0.05 and because the sample mean was located in the region of rejection, the probability of obtaining a sample mean of this size from the sampling distribution represented by the null hypothesis was less than 5 in 100. That's a mouthful. It's completely summarized in this notation, right? So this is a very efficient way to communicate the results of our experiment. Okay, now what are the two kinds of inferential errors that we can make in our decision making? Now, when we say inferential, all research that employs statistics, inferential statistics, involves trying to make what amounts to an educated guess about a population from sample data. Okay, so when we conduct an experiment, we're not dealing with the entire population. We're dealing with a sample that effectively stands in for the population. So there is the possibility that the conclusions rendered in a research study may not, in fact, reflect accurately what's going on in the population, right? It could be two different state of affairs, in which case our inference about the population based on what we observed in the sample may be incorrect. So let's talk about where things can go wrong. Okay, so this generally falls under the heading errors in decision making. All of our decisions using statistics are probabilistic. That means our decisions are inferential. We have limited amount of information about the population because we're working with a sample of data. So it's always possible that the decision we make with regard to the null hypothesis could be in error. As an example, although it's unlikely that we would have randomly sampled a mean from the null distribution, the sampling distribution, that is located in the tail of that distribution. It's not impossible that that could happen, okay? Unlikely events do happen, okay? They may be highly unlikely, low probability of occurring, but they do happen. So even sample means that are located in the tail of the distribution, of the sampling distribution, have a small probability of being chosen by chance. But that's different than saying they have zero probability of being chosen. So the first kind of error that we can make is called a type 1 error. And this involves rejecting the null hypothesis when it should have been retained. In this situation, we conclude that there's a relationship between the independent and the dependent variable in our study, when in reality in the population, there is not one. Okay? Call this a false alarm. And there goes our fire truck off to the rescue of somebody. So a false alarm basically means that we've claimed a relationship to exist when in fact it really does not. So, as examples, claiming that the pill has an effect on improving IQ when in reality it doesn't. Claiming that a treatment works when in reality it doesn't. Claiming that an educational intervention improves test grades when it really doesn't, right? All of those would be false alarms. Now, because a type 1 error can only happen when the null hypothesis has been rejected to begin with, the probability of making a type 1 error equals alpha. So think about it. Alpha is the size of the region of rejection. We can only reject the null hypothesis if the sample mean falls in the region of rejection. Therefore, our type 1 error rate will be equal to the size of the region of rejection. Now, does that mean you'll know when you're going to make, or when you have made, a type 1 error? And the fact of the matter is, you don't. You could have the best designed study in the history of psychology, okay? But because you're using statistics and you're working with a sampling distribution, the fact of the matter is 5% of the sample means that could be drawn by chance out of a hat randomly if you ran this experiment infinitely. 5% of those sample means will fall in the region of rejection, no matter the design of your experiment. That's just the nature of probability. So as a result, the type 1 error rate equals alpha. No matter what your result is in terms of rejecting the null hypothesis, the moment that you reject the null hypothesis, you run a 5% chance of rejecting incorrectly. In other words, what you observed in your study is not true for the population. 5% chance. So it has nothing to do with errors in design. It has nothing to do with running an experiment incorrectly. It's just a function of the probability and the way that we create sampling distributions and make the decisions that we make in statistics. Now, a type 1 error can be, not a good thing, right? Because basically you'll publish your article, it'll get out there in the literature, people will try to replicate your finding, and most likely they won't be able to replicate it. In which case, at some point, somebody's going to say, yeah, we just don't think that that's actually true, and that those results represent probably a type 1 error. Now, there's also what we call a type 2 error. And type 2 errors are a little bit more insidious than type 1 errors. So a type 2 error occurs when a researcher fails to reject the null hypothesis when it should have been rejected. In other words, you missed something, right? So it's kind of like this. Ball hits off the glove, off it goes. This is a miss. In a type 2 error, there really is a relationship between two variables in nature, in the population, but your study found that there wasn't. So the relationship between the IV and the DV really does exist, but the researcher failed to detect it, okay? Now, in our example, that involves claiming that the pill does not increase IQ when in fact it actually does, which could be kind of sad, right? I mean, it would be nice to be able to have this nice, easy, as long as it's not harmful, nice, easy way to boost your IQ by a few points. But if you didn't detect that in your study, then that would be a miss. Now, we're using, in some ways, kind of a whimsical example here of IQ and a pill, but this could get much more serious, right? If we think about, for example, claiming that a new treatment for cancer does not improve mortality rates when it actually does, right? If we miss that finding in a study, that has implications for people's lives, okay? So that's a real challenge. Claiming that a new educational program does not improve grades when it actually does. Now, earlier I said this is kind of an insidious thing. It's kind of, the implications of type 2 errors, you have to think about a little bit more than type 1. Type 1 is easy to conceptualize, right? You say you found something, but it's really not there. This happens all the time. We see that all the time in the literature. But type 2 has a different sort of effect. Because in type 2, you're saying, hey, there is no relationship between two variables, but in fact, there is one. In science, that can have the effect of stunting research in an area, right? So imagine you're a researcher and you found out from a colleague, oh, we tried to run this experiment, but we didn't find anything. It's not worth looking at. What does that do? That means investigation into an area stops. With type 1, on the other hand, basically you've claimed to have found an effect, and then other researchers, if science is working, should try to replicate your results. So there's additional study. Type 2, not so likely, right? In a type 2 error, you're claiming there is no relationship, so why would a researcher pursue that? Okay, they're going to take your word for it. They're going to say, okay, yeah, I looked at your study. It really looks like there's no effect. We're not going to pursue this anymore. And that could potentially stunt an entire area of fruitful research if a type 2 error has been present. So here's, think in terms of this matrix. This is a useful matrix that I've seen. I wanted to make sure that you had a chance to take a look at. Think, first of all, about the situation involved in experimentation. We have the experimenter's decision. This occurs as a result of a study. And then we have the actual situation in nature. So you can think of this as decisions surrounding the sample, and this is the situation surrounding the population. Okay. Now the experimenter's decision is really one of two choices, right? You can either reject the null hypothesis, or you can fail to reject or retain the null hypothesis. Sometimes you'll read in studies language that says something along the lines of, well, we had a marginally significant effect, like our p-value equal 0.06. That was marginally significant. Or the results were trending towards significance. It didn't satisfy the 0.05 criterion, but it was really close. So it was trending towards significance. Okay, what I want you to think to yourself is hooey. That's all bull hooey, okay? And it's bull hooey because the way null hypothesis testing is set up, it's not to have gray areas. That's the whole point. You don't have gray areas where you have trends or you have marginal significance or something like that. No, in null hypothesis testing, you either reject the null or you fail to reject the null. There is no gray area, okay? And similarly, in the real world, we would see either an effect for two variables, that an effect exists, that there's a relationship between two variables, in which case the null hypothesis is false, or no effect, in which case the null hypothesis is true. So if we create this 2x2 table, what we find is that two of those quadrants represent correct decision making. So in an experiment, I could reject the null hypothesis, and in fact that would correspond to the state of affairs in reality, that there is a relationship between two variables. The null hypothesis is false. In that case, I've made a correct decision in my experiment. Okay? Or I could fail to reject the null hypothesis and say that there's no relationship between two variables, and in reality there's in fact no relationship, no effect. That's also a correct decision. So as much as possible, we want to be on this diagonal of green, right? That represents correct decision making. But we might not be. We might make a type 1 or a type 2 error. Okay, in a type 1, we've rejected the null in our study, but in fact there's no relationship, no effect, no relationship between the two variables in the population, in the real world. Or we could retain, this would be type 1, or we could retain the null hypothesis when in fact an effect does exist, there is a relationship between two variables. That then becomes type 2 error. So the hard thing about science is that we will always know this part, right? Because we've done the study. We've decided to reject or retain the null hypothesis. So we always know this. The problem is we don't always know this, right? We don't always know what exactly is going on in the population. The only way that we get to that is through additional experimentation. And even then, it really comes down in some ways to a matter of consensus, right? Whether there are enough studies to help support the idea that whatever we decide in our study was in fact the correct decision to make. Okay, so type 1 error, the probability of type 1 error was equal to alpha, 0.05. So you might ask, well, what's the probability of type 2 error? And your first reaction might be to say, okay, well, if probability of type 1 error is 0.05, then the probability of type 2 error is 0.95, right? You add those together, you get 1.0. Sounds interesting. It's absolutely wrong, but it does sound interesting. And it should sound wrong to you because if you have 0.05 plus 0.95 equals 1.0. Basically, what you're saying is you have a 100% chance of making an error in your results. It's either going to be type 1 or it's going to be type 2. And if we have a 100% chance of making an error in our results, why are we doing this, right? Why are we engaged in statistics to begin with? Well, calculating type 2 error rates is harder than calculating type 1 error rates, okay? And we're not going to go into all of the details about how to do it because it does involve some calculations that go well beyond what we should do at an undergraduate statistics class. But let's leave it at this. Type 2 error involves something that we call statistical power. And what power refers to is the probability that the statistical test that we're using will correctly reject a false null hypothesis. In other words, make the right decision about the null hypothesis. So power is essentially a probability statement, but it's not easily calculated the way we did with type 1. With type 1, we just looked at the size of alpha. That was easy because you have to reject the null to begin with in order to make a type 1. Power depends on a lot of things, and it gets more to the design of the experiment. Type 1 error really involves just statistical properties of normal distributions. Type 2 involves a lot of decision making about how the experiment was designed to begin with. So the likelihood that a treatment effect will be detected if one really exists, that gets to the heart of power. And there are a lot of design features that increase the chance of committing a type 2 error. Small sample size, right? One of the things that you know already is that if your n, your sample size is low, then your sampling error goes up, right? So, when you talk about standard error, that gets bigger as your sample size gets smaller. They're inversely related to one another. Probably the most common problem we have in psychology is small sample size, that our studies are just underpowered, which makes it difficult to reject the null hypothesis. It makes it more likely that we'll create or commit a type 2 error. High levels of variability in the population. Okay, if we're dealing with subjects that are really different from one another, that introduces noise into our experiment. In animal studies frequently will be very careful about the strains of animals that are used in the study. Why? Because if you introduce different strains, then you get variable behavior. If you get variable behavior, it's hard to find an effect. Okay, best example I can think of is imagine you were in a room and you were looking at the thermostat and you looked at it 1 minute and it said 72 degrees. Come back a couple minutes later, 76 degrees. Come back a couple minutes later, 64 degrees, okay? And those numbers were all over the place. Well, that's introducing variability into the measured outcomes, right? It introduces variability into scores. So if there's all this variability in measurement, okay, then how would I know if, for example, a heater that I put in the room really increased the temperature of the room? I couldn't rely on the thermostat, could I? Right? Same thing happens with populations. Okay, that example involved the measurement of temperature. But you might as well just as easily say, okay, I'm doing a study and I'm looking at treatment effects on individuals with alcoholism. Okay, so I have this group of folks and all they've done is abused alcohol. But then I introduced a whole bunch of subjects into the study who not only had alcoholism in their background, but they also had opioid abuse. Right? Those folks look different, right? They have different kinds of problems than folks who are just alcohol dependent. But now they're all put into the mesh together. Would I expect that my treatment outcomes for the folks with alcohol dependence might look different from my treatment outcomes for the folks who also have opioid dependence? Maybe. And if that's the case, how would I ever really know the effect of my treatment just with folks who have alcohol dependence, right? So high levels of variability in the population, generally speaking, make it difficult to reject the null hypothesis. Unreliable measurement instruments that cannot detect change in the dependent variable lead to the same kind of problem. They actually introduce really weird outcomes to our statistical tests. So if our thermostat is unreliable, it's hard to detect real changes in temperature. Okay, if we have an IQ test that doesn't really measure IQ but measures something else, say socioeconomic status, okay, then how do we know whether scores reflect intelligence or how well off you were in your childhood? The kind of statistical test you run will make a difference on type 2 error. So you're going to be reading about in your text one-tailed tests and two-tailed tests. And one-tailed tests are more sensitive because what we do is we load the region of rejection into one side of the sampling distribution. That has the effect of lowering the z-score required to reject the null hypothesis. In other words, the z-crit gets smaller because all the region of rejection is on one side of the distribution. I'm not going to spend a lot of time talking about that because you'll be reading about that. But one-tailed tests are in fact more powerful than two-tailed tests simply because the threshold is lower for rejecting the null hypothesis. Okay, instead of it being plus or minus 1.96, it's only 1.65, but only on one side of the distribution. So that actually makes it a little more powerful. We could adjust the alpha level. By convention, alpha equals 0.05. And that is a more powerful test. In other words, more likely that we will reject the null hypothesis than, say, an alpha of 0.01, when we reduce the size of the region of rejection to just 1% of the area under the curve in the sampling distribution. So there's really no easy way to calculate type 2 error in power. I mean, that's a graduate level statistics question. If you go to grad school, you're going to find out a lot more about power. But it's, again, not nearly as easy to calculate as, say, type 1 error. Just remember that power is inversely related to type 2. The more powerful your design, the more powerful your experiment in terms of all these different attributes, the better designed it is, the lower your type 2 error is going to be. So the more power in a study, the less chance of making a type 2 error. So what does that mean? That means, as best you can, have a big sample size. Have a sample size that's adequate to detect when an effect is present. As much as possible, reduce the amount of variability in your sample. Try to have subjects that are selected carefully. Typically, we use inclusion and exclusion criteria to do that. Have reliable measurement instruments. Okay, that's one of the reasons why in your lit review, when you're describing the measures that you have in your study, you want to report the reliability and the validity and so forth of an instrument. Okay, make a good decision about the type of statistical test you're going to use. To use a one-tailed test, you have to provide justification for that before you even run your experiment. Okay, and make sure your alpha level is appropriate. 0.05 is appropriate. That would be accepted within a journal for sure. But if you wanted to put alpha at 0.10, you better have a good reason to do that, because reviewers will say you run a higher risk of committing a type 1 error if you, in fact, increase the size of the region of rejection. So we have to balance type 1 and type 2 error. And if we decrease type 1 error, we actually increase the rate of making type 2 error. So there's a trade-off. It's not like, we're going to get rid of type 1 error or type 2 error. There's really a trade-off. So if we set alpha equal to 0.01 rather than 0.05, sure, we reduce the chance of a type 1 error, a false alarm, but we also increase the chance of missing something. So we increase the type 2 error rate. So this is a useful distribution for us to see. You can see what happens to the critical region, the region of rejection, as we play with alpha. So at 0.05, alpha is at plus or minus 1.96 if you're running a two-tailed test. At 0.01, look what happens. If alpha is 0.01, in other words, only 1% of the area under the sampling distribution is in fact the region of rejection, then the z-square required for the sample mean to exceed is plus or minus 2.58. And if you go to 0.001, you have to have a z that is plus or minus 3.30. Okay? And as those cut points move further into the tails, that means it's less likely you're going to reject the null hypothesis. So your type 1 error rate goes down, but your type 2 error rate goes up. Okay, so that takes us through null hypothesis testing. I really hope that you got it and you understand. If not, please make sure to stop by during office hours. We can chat about it a little bit more. But to close out this lecture, let's talk about what's called effect size. Because at this point, we've talked about p-values, probability values, the likelihood that we would observe a sample mean in the tail of a distribution, sampling distribution, simply by chance or measurement error, sampling error. And that's really a statement of reliability, right? If we're saying, hey, the probability is 0.01, we're saying, hey, that's a pretty reliable finding. The chance that I would find this result by chance is only 1 in 100. But it doesn't really tell us about the magnitude of the effect, like how strong the effect is, okay? So we need a different kind of statistic to look at that. And that's where effect size comes in. So there's more to life than p-values. Rejecting the null hypothesis only tells us that a sample mean is unlikely to have been drawn from the sampling distribution represented by the null hypothesis, in other words, the untreated population. And because it's a dichotomous decision, either we reject or we do not reject the null hypothesis. Null hypothesis testing does not tell us the magnitude of the treatment effect in meaningful terms. It only tells us the probability of observing a given sample mean from the null sampling distribution. That's where Cohen's d comes in. Cohen's d is pretty easy to calculate. We're just going to take the difference between the sample mean and the population, we'll just call it the mean difference, and divide by the standard deviation of the population. So it describes the size of the treatment effect in standard deviation units. Excuse me, I gotta get my coffee again. So let's think back to our original experiment. Here's our pill, looks the same. Cohen's d is expressed as follows. The sample mean minus mu divided by sigma. In this case, it would be 106 minus 100 divided by 15, because that's the standard deviation of IQ squared. That becomes 6 over 15, or 0.40. Now, what does that 0.40 mean? That's the question. So the way we're going to interpret that is to say, people who took the pill scored, on average, 0.40 standard deviations higher on an IQ test than people who did not take the pill. Now, why do we say in standard deviation units? Because we're dividing by sigma, which is the standard deviation of the test. So by definition, this 0.40 has to be in standard deviation units. So in a z-table, a z of 0.40 corresponds to 0.1554, the area between the mean and z. Thus, we could conclude, if we look this up in a z-table, that the effect of taking the pill was to increase the average person's IQ from the 50th percentile, which is where mu is, to the 65th 0.54 percentile. In other words, we just add 0.50 to 0.1554. That's a pretty good effect. If on average you're jumping 15 percentile points, not bad. Okay. Now we do have ways of evaluating or even labeling effect sizes. Okay, so effect sizes that are from 0 to 0.2 we call small effects. In other words, the mean difference between the treatment group and the control group, for example, is less than 0.2 standard deviations. A medium effect would go from 0.2 to 0.8, and that's a median a mean difference around 0.5 standard deviations. And then a large effect is anything over 0.8. So anything over 0.8 standard deviations becomes a very large effect. We can represent this effect by looking at two overlapping distributions. Okay, keep in mind we had a mean of 100, standard deviation of 15 in the untreated group. This is what we expect out of folks if the pill doesn't work. The blue distribution represents the distribution of scores when the pill did work. So let's imagine that in this example, rather than having, let's say the sample have a mean of 106, like we showed earlier, let's say they had a mean of 115. What that means is that the mean of the treated group of 115 fell one standard deviation above the mean of the untreated group. So Cohen's d is going to equal 1.0. Okay, that's a really big effect. It's much bigger than 0.8. Okay, so we're expressing this visually as effectively a mean shift to the right, with a normal distribution in the population, and a Cohen's d of 1.0. Okay, big picture, and I'm glad it's here because I think my voice is giving out as we get to the end. We always test the null hypothesis. Because we are using samples, we can make errors in generalizing about the population because we're making inferences from the sample to the population. The errors that we can make, type 1, type 2. Low power makes it hard to detect an effect, increases our type 2 error rate, and also has the potential to stunt future research. P-values tell us the reliability of a finding. Effect sizes tell us the magnitude of the finding. So you can kind of think of p-values as a statement of how reliable the result is. And effect size, in many ways, tells us how important the result is. I think that's about it. Hope you enjoyed that. See you in class.